All right, so when you have a collision, it can be a completely elastic collision. That's the type of collision where both momentum and kinetic energy are conserved. So a super ball, it doesn't quite work exactly, but if you drop a, really bouncy rubber ball and it were to return to the same height from which it was released, you would say that is a completely elastic collision. If you drop a basketball and it doesn't quite bounce back up to the same height as it was dropped, then that's a somewhat inelastic collision. And then if you drop a basketball and it just smushes on the floor because it doesn't have enough air in it, then that's a completely inelastic collision. Elastic, both momentum and kinetic energy are the same before and after. We say they're both conserved, and an inelastic collision is one where kinetic energy is lost during this collision, but momentum is conserved. The other type of collision is an explosive event. This would be an explosive event. The initial momentum is zero, the final momentum is zero. The initial kinetic energy is zero, the final kinetic energy, because there's no negative kinetic energy, the final kinetic energy is much bigger than it was initially. That's an explosion. When you have fireworks or something exploding, that's an explosive event. Now, things can get really weird when we try to apply this over 2 dimensions. We will have a question with a car accident where we're going to say that it's a inelastic collision, so that momentum is conserved but kinetic energy is not. This is a case where we have a collision in 2 dimensions where both momentum and kinetic energy are conserved in 2 dimensions. This is really complex to keep track of everything. We have one ball that is carrying both some negative y-axis velocity and positive x-axis velocity into the collision. So that's negative y-axis and positive x-axis momentum that has to be conserved both before and after the collision. The blue ball has only x-axis velocity and momentum. When they collide and go apart, we're given some information as to their final trajectories, and then we would both conserve momentum and kinetic energy. It would be long and hard. All right, at some point we have to talk about this concept of center of mass. So now's as good a time as any. When we have multiple masses that are connected somehow, the center of the object, the geographical center, the geometrical center of the object, may not actually be the center of mass. So here's just one example of, if you have 2 masses and the green mass was a lot more massive, then we would find the center of mass is a lot closer to the green mass than it was to the other one. So we have an equation. The center of mass is m1 x1 plus m2 x2 divided by m1 plus m2. That will give us an answer. Where is the center of mass in this system? We can find that value explicitly. We can also find the center of mass velocity for an object. If something was moving, we'd be able to find that. And that'd be another tool. Can also do it for acceleration, but then it's just getting weird. Okay, that takes us enough through this material that you should be able to tackle the homework, and this will be made a lot clearer in a lab activity than it ever would be in a lecture. So hopefully you'll get to experience this in labs soon.